So in this talk, I'll be showing you how to do distributed deep learning using MXNET to get very high level of efficiency, as well as have a flexible programming framework with a large degree of portability. And I'll also show you how this can be done efficiently on the AWS infrastructure. So regarding my background, I'm a principal scientist at the AWS deep learning team. I've been there since last October, and before that I've been a faculty at UC Irvine looking into large-scale machine learning. And MXNET is a package that we're actively developing at AWS and enabling it on the AWS cloud. So these are exciting times to be working in AI and machine learning, right? So there are three main factors that have led to this deep learning revolution. In addition to the core algorithms, it's really the presence of a large data set and compute power that has made this revolution possible. And so as we try to think of even more challenging tasks, we need to keep in mind on how to solve the data problem as well as the compute problem. And in this talk, I'll be addressing the latter on how to scale up computations efficiently and how to do memory optimizations for these very large models. Right, so indeed, deep learning has now touched almost every domain. Right, so it started with efficient image understanding. When we solved the ImageNet competition using deep learning and obtained much better performance than the classical methods, that's when machine learning researchers got very excited about the potential that deep learning has. And since then, it has touched upon speech recognition, natural language understanding, and the latest one is autonomous driving or self-driving cars. And these tasks are increasingly more complex as we try to apply deep learning in them. So the canonical computer vision task is one of understanding images, right? So this is the scene recognition task and detecting the objects in these images, right? So in this example here, if you're given this picture, the kind of outputs you'd like to see are various categories that are present in this image along with the corresponding confidence levels. And this is the Rekognition service that Amazon AI has recently launched that will give you this in real time, for enterprise level settings. And so, in this setting, we are asking, can you, in an automated manner, get these labels for any input image? So you can also be more specific about the categories for a subclass of images that are the faces. So you can think about emotions that a face has, or whether there's sunglasses and so on. And you could use this for face detection and verification in a number of applications. So the machinery behind deep learning in computer vision is this convolutional neural network. So the basic idea is there are multiple layers of operation before you make the final decision on what categories are present in this input image. In this example here, this is the input image, and then the output is something like, with 85% confidence, there is a dog in this image, right? And the convolutional layers here are providing processing of spatial information and progressively extracting more informative features for categorization of the input image. So the intuition is you need depth, right? So you need deep learning to be deep and not shallow. because you need the simple features to progressively compose into more complex ones that mirror the real world images, right? So that mirror the objects that occur in these real world images. In this example here, taken from Zero et al. Paper, right? So you'll see that the first layer will contain filters that can detect very simple features. So think of like lines at different angles, right? So if you just look at the first layer of your network that feeds from the input, you can only detect simple shapes. But then as you go higher up in the layers, more complex features get activated. So for instance, in layer 4 here, there's the face of the dog, right? So it gets strongly activated in this layer. So the intuition is you need to go higher up, sufficiently higher up in the layers, right? Going from input to multiple layers of processing to get increasingly more complex features that can capture real world objects or features that occur in natural images. And this is what enables it to then efficiently categorize these objects with high accuracy. And so depth is an important aspect when it comes, that's why the term deep learning. And when it comes to images, convolution is also an important feature, because you want to have convolution to have small filters run through an arbitrarily large image and extract features as you go along, right? So the idea is intuitively you're sliding this filter all across the image, trying to detect the features that are present in the image. And to do that, convolution enables it because it's a translation invariant operation. And so that's where convolution is useful when you're dealing with images. So there are also another class of deep learning models called the sequence models. So in this case, what you want to do is take in a variable length input and potentially also have an output that is of variable length, right? And this is where you maintain an internal state that is recurrent, that is, it feeds onto itself and maintains memory of the previous operations. And so this enables you to encode any variable length input and output have a variable length output. To give you an example here, right, so you can have architectures such as an encoder and a decoder for the example of question and answering. So you have a question, your task is to output an answer, and what you do is once there is a question, you try to encode what the question is about, right? So you come up with this hidden state representation of the question. And this representation is then fed to the decoder, right? So that has to emit each word in the answer. And to do that, you need to maintain memory within the decoder, right? So you need to go from one state to the next, but you also need information from the encoder to be fed into the decoder. And so there can be a lot of complex architectures when it comes to these sequence models, but the basic ingredients are having notion of memory, right? So this is the hidden state that propagates forward in time, or more generally could also propagate backward in time. You can have bidirectional models that propagate from both directions. And then typically you may also have an encoder and a decoder. The job of the encoder is to find a representation of the input sequence, while the job of the decoder is to use this representation and generate an output sequence. And so there's a whole set of models that are arising from deep learning. And at Amazon, we are using machine learning and deep learning in just countless number of ways, right? So you can think of all the way from fulfillment centers that are now having interaction between humans and robots and how to do that efficiently, to predicting the supply chain and when, how people are ordering things and when product may go out of order, right? So there's a whole set of things to be done in fulfillment and logistics. And Amazon uses machine learning extensively there. And there is, of course, the whole set of tasks related to search and discovery of, of product, of services, of visual search. So, and that's where deep learning can make it a lot more efficient. And we're always using machine learning to improve our existing products as well as design new products. Of course, some examples of this, the most famous one probably is Alexa, right? So it now has increasingly more capabilities on being able to recognize a range of voices, from even across the room with other, background noise, and be able to deliver on a number of tasks that it is told to do. Amazon Go is an exciting new venture where if you've been to Seattle, there is a store with no cashiers, right? So you really feel like you're shoplifting there. So you go, you pick up a thing and just walk out of the store. And to enable this, deep learning is really at the core because you need to detect what people are doing in the store and what items they are picking up. And so that's where, deep learning also done, over large amounts of video data and delivering the results in real time becomes a very big challenge. So at Amazon AI, as part of the AWS division, our mission is to enable AI tools and services on the cloud. And so today I'll talk about, in particular, the Apache MXNET package that is the deep learning engine of choice at Amazon and has a number of exciting features. At the same time, we're releasing a number of AI services. These are managed services aimed at enterprises that can harness the power of AI without going deep into training, collecting data, training on their own, right? So this lets you get answers in real time on large scale data. So recognition, as I mentioned before, enables image recognition, face recognition, scene recognition in real time. So Lex is really what's inside Alexa, right? So literally, if you take the A on either side of Alexa, that's Lex. And so what Lex lets you do is quickly build chatbot interfaces for your business. So you can easily describe how this chatbot should interact with the customers, and you can harness the power of Alexa. So meaning you can integrate your own set of rules with the knowledge graph of Alexa and be able to get voice inputs and voice outputs using Lex, in addition to text input and output. So Polly is the real-time text-to-speech service. I encourage you to go try this. It has a very large range of voices and languages and has real-time performance, but with also the ability to customize. So let me now go deeper into how MXNET is enabling large-scale deep learning with high efficiency. Right, so the picture I've shown here is the Inception v3 network. It's one of the state-of-the-art networks for computer vision. So without going into details of what each of these blocks are, you can see from this picture that there is a large set of connections and a high level of complexity in this network. right? In fact, there are more than 100 layers in this network. So you possibly cannot program this from scratch, right? So you need efficient network primitives and operations that lets you quickly prototype and develop such complex models and also be able to run them in large scale during production. So the question is how to enable efficient computation at scale. Right, so indeed GPUs are the framework of choice here because they offer much higher flops compared to the CPU. And they're also highly optimized for the matrix operations that occur in deep learning. And the other aspect that I'll cover is memory consumption. So as these models become increasingly bigger and more complex, it won't be feasible for us to store them in memory. Right, so that becomes a bottleneck, and then the question is, can we do efficient trade-offs and enable training and inference of these large-scale models? Right, so what are some features in a deep learning package to enable all these operations? As I said, the first one would be programmability. So how can we easily enable these complex architectures and make the job of the programmer easier? The second one is portability. So how do we enable the same deep learning code across a range of platforms, maybe even different devices such as IoT devices, right, with limited amounts of memory, and be able to adapt to different memory settings? And the third one is efficiency. Right? So how do we do efficient large-scale both training and inference on these models? So ideally, if you ask 4 GPUs instead of 2, right? So you scale up your number of GPUs, you would like your throughput to also correspondingly scale. Right? So, but this is the ideal setting, right, where you have 100% efficiency, but then you expect in practice to be close to this ideal. And this is when you can build increasingly larger models, right, by scaling up. Otherwise, it won't be feasible. And so indeed, there are a whole set of frameworks available today for deep learning, and all of them are enabled on AWS infrastructure. Right? So we support all of them very well. But at the same time, we recommend MXNET as the framework of choice at AWS. We are actively developing on it, and we'll also see how it has a high degree of efficiency. So if cost is a concern for you as you're running these deep learning applications on the cloud or even on your local machines, then MXNET would be a framework that you should consider. And I'll show you more details on why that is the case. Right. So the two main features of MXNET is it is the most open source of all the packages. We have the Apache certification. And the other one is, as I said, we are actively developing and enabling it to work very well with the AWS infrastructure. So let us now see how MXNET scores high on programmability. Right. So depending on your background, you may choose any one of these languages. Right. So while Python is a popular language with data scientists, statisticians may prefer R. So Scala may be for people who do extensive Spark work. Given this heterogeneity of choices of programming, right, so how can we ensure that all these communities can harness large-scale machine learning and get good efficiency? And so the way to do this is to enable all these front-end languages, but then have an interface that connects them to efficient back-end libraries. Right? So this includes the CUDA deep learning library as well as the MKL library for CPU instances. And that's what we've done in MXNET to build this efficient interface that supports all these choice of languages. And the other aspect is the style of programming. So the simplest style of programming is the imperative one. So what I've shown here is just a simple set of Python code, right? So you're declaring some vectors here and then just manipulating them, doing some simple operations. So the challenge with this imperative style is that it's bad for performance, right? Because you're interpreting line by line, the system has no idea on what is coming next, so it cannot optimize for it. On the other hand, it's very easy for the programmer because you can just keep writing the exact set of operations you want sequentially, right? So while it's easy for the programmer, it's bad for optimization, it's bad for parallelization, right? It's bad for efficient memory allocation. And so that's the issue with these imperative style of programming. And that's why many deep learning libraries prefer the declarative style of programming. So in this, what you do is you declare the variables first, right? Then you specify the set of operations and you have the compilation process. And because of this, there is access to the computation graph. And so once you have the computation graph, you can now do auto parallelization, you can do efficient memory allocation. So for instance, in this simple example, you know that the result of A and B here, this multiplication, will be replaced in the very next step with another operation. So you don't need to allocate separate piece of memory for C and D, right? So you can overwrite that. And so this framework will really require the symbolic execution, right? It needs access to this computation graph. And on the other hand, this framework is less flexible. It requires the programmer to carefully declare all the variables. It results in longer programs. And so declarative style is kind of more burden on the programmer. So what do we do in MXNet? So what MXNet does is it allows you to mix both these styles of programming. So in the imperative style, you can declare ND array. So this is nothing but the multi-dimensional array, right? So similar to the NumPy. So you can write this in imperative style. And then what you can do is you can bring that in to your symbolic execution. So in this snippet of code, what we are doing is declaring the network architecture, right? So what should the network look like? There is a fully connected layer, there's a softmax output, and so on. So we are declaring the network architecture, but then we can also feed in the data that was earlier manipulated in the imperative style. So you can mix these two flavors of programming. So you can also do the opposite. You can declare your network architecture before and then bring that into an imperative style of programming. And what is happening here is the gradient update, right? So you're updating your parameters using the gradient and this learning rate here. And typically what you want to do is have the network definitions, the network architecture be in declarative style, because that's where there is room for a high level of optimization. On the other hand, gradient descent and all these other manipulations, right, can be written in imperative style, and it's much easier and cleaner to do it that way. And so MXNet is unique in that it offers you to do both, and so you can decide as a programmer what works best. Right, so now let's see how portability is also easily supported in MXNet. So MXNet supports amalgamation, which means you can take all the dependencies into a single source file, and you can compile this on any platform. So anyway, this is a simple demo that shows how you can deploy MXNet on JavaScript and then enable computer vision task on your smartphone, right? So you can quickly build this on smartphone or any other device and make it portable across different platforms. The other aspect, as I said, is memory optimization. So if you're doing training on these large models and memory is a constraint, you want to be able to specify what you want to store in memory and what you want to recompute. So what I've shown here is the standard forward and backward pass in a neural network, right? So in the forward pass, what you do is you take in the input and then you compute activations in each layer here. And in the backward pass, what you do is you take information about the activation, right, and then you update the weights, right? So you go back through the layers. And this is coming from the chain rule of derivatives. So this is the standard operation. And in this operation, you need to store all the activations of all the layers. So now if you have 100 layers, you need to store all of them in memory, and this is not going to be feasible in many settings. Excuse me. So instead, the option is now to do memory allocation to only some set of activations, right? Meaning you segment your neural network and only store some of them, some of the layers in memory. And what you do for the others is recompute. So you start with the nearest node that was stored in memory, and then you go forward and then recompute the activation when it is needed for the backward pass. And so this way, you can now trade off memory for extra computation. And in most cases, this extra computation is just one more forward pass, and this doesn't add much. Right. On the other hand, you can improve your memory requirement from linear in the number of layers to, in fact, square root of the number of layers. Right. So to give you some numbers, the ResNet, before it was 130 GB, but after this scheme, you can reduce it to as little as 4 GB. Right. So the idea is you're not doing any compression. You're enabling exactly the same set of operations. But you are deciding which ones you want to store in memory and which ones you want to recompute. And MXNet easily enables you to do these trade-offs and come up with efficient memory allocation. So let us now see how it scores high on performance. So indeed, if you are to write parallel programs from scratch, that is a big pain. Right. So I don't know how many of you have used MPI here, but that was the programming framework of choice before deep learning came along. Right. So you would specify every single operation and say how the communication occurs and so on. But in this example here, you can see that this just is not scalable for the deep learning setting. Even with just 2 GPUs and a CPU, having the forward and the backward pass, right? And you're aggregating that in the CPU is just too many operations. So intuitively, what is happening is you take the data, you're dividing the data and sharing one part of it with the first GPU and the second part to the second GPU, right? And then each GPU, does its own forward pass. And what happens is then you share this information, the gradients, right? So as you're doing the backward pass, you're sharing the gradient update into the CPU, and the CPU aggregates and does the set of operations, right? So don't worry about the details, but you can see that this is very complex. So we don't want to worry about each single operation. So how MXNet handles this is through a hierarchical parameter server where there are GPUs at the lowest level, but aggregation happens in a level 1 server, which is a GPU itself. So it's much faster to communicate among the GPUs than to the CPU, right? So first aggregation happens at the GPUs, and then you send it up to the CPU. So we have a number of benchmarks on this GitHub website, but I'll just show you a flavor of how they look like. So what we see is on a 16 GPU instance, so this is the P216X large instance on AWS, we see 91% efficiency for the state-of-art networks, the Inception and the ResNet, right? So here I'm doubling the number of GPUs. I expect my throughput to double, right? That's the ideal setting, and we are very close to that ideal. So there's very little amount of overhead when it comes to running this on MXNet. In fact, we can go even further and take 256 GPUs, right? So in this case, I'm taking 16 instances of P216X large and putting them together. So in this case, we see that there is a slight drop in efficiency, indeed because it has to now go through the network as well, right? So these are separate machines. And still, we don't lose much when it comes to efficiency. And the details are on the GitHub website, but the idea is you can get high level of efficiency on hundreds of GPUs using MXNet. Right. So the other aspects at AWS is we want to make deep learning seamless and easy to run, right? And one aspect of that is the Amazon machine images or the AMIs, right? So which means all the tools are set up. So a variety of packages, MXNet as well as TensorFlow and Torch, right? All these packages are already installed, made up to date. You have the drivers and the, all set up, both the GPU and the CPU instances, as well as the Jupyter notebook and so on. So everything is set up for you, so it really gets you going. Yesterday we had a long tutorial on how to actually set up and get this going. So I'll just very briefly show you how to do this. This is a quick video. I mean, the goal is not to understand every detail of it, but to see that how it has gotten very easy to run deep learning on the AWS cloud using CloudFormation template and the deep learning army. So it's just a matter of few clicks. You don't have to set up your own cluster. You don't have to install anything. Everything is available to you beforehand. So what we are doing is now going to CloudFormation and creating a new stack. And so this is where we can take the predefined CloudFormation scripts, right? So this will already configure your machine, so you don't have to worry about them. You can select what kind of instance you want. P2 is the GPU instances, right? So things like SSH location and how many workers you need, right? And you can name your stack, and that's about it, right? So you, of course, need to specify the key value pairs and the permissions, and you have your stack going. And once you have this, right, then you can track the progress, and you can SSH into that machine and be able to quickly get your deep learning going. So I will not show all the details of how it does, but I just wanted you to see that it's now gotten really easy to run deep learning on AWS. I've talked to many people, and they're not always aware of armies and CloudFormation templates. So this really makes it a lot easier to get started on deep learning on AWS. So with respect to MXNet, we are adding a lot of features. We are making it amenable to all other forms of machine learning in addition to deep learning. This involves having sparse data types, right, which are not present in traditional deep learning but will be relevant for other operations. And in the last few minutes, what I want to show you is how we are also enabling new algorithms that involves tensors, right? So tensors are much more than just a multi-dimensional array, right? So just as we have matrix multiplication, we can do multi-dimensional manipulation using tensors. And with deep learning, what we are manipulating are really tensors rather than matrices, right? So we can get a much better efficiency with that. So just to give you an example, this is the classical MXNET architecture for image classification. And what's happening is you're taking the input image, right? It's really a three-dimensional object because you have the width, height, and the number of channels. And the number of channels in the typical case is the RGB for the input, right? But as you go through the layers, you again grow your number of channels, right, depending on the number of filters you have. So in each step, what you're doing is really processing tensors. But then in the MXNET, what's happening is when you finally want to get the classification, you're flattening or converting them into matrices and doing operations, right? So you're losing the structure just when you're in these fully connected layers. And so what we proposed instead was to have a tensor contraction and a tensor regression layer. So what you're doing is you're taking in a tensor input and you're doing a contraction, right? So rather you're coming up with weights for each dimension of your tensor, and the output is still a tensor. And to show how this can lead to much more compact networks, right? So we even get a better accuracy compared to the baseline with a large degree of space saving, right? So it's now 44% space is saved, or the number of parameters are saved by using these tensor operations. And so these are enabled in MXNET, and we'll be adding more such capabilities to MXNET. And so as I mentioned, we at Amazon are involved in a number of efforts behind having AI services in addition to MXNET, which is the deep learning engine. And stay tuned for more news on this front. So I also want to point out that at AWS, we have a cloud credits program, for startups, for researchers, for developers, right? So there's a whole set of programs designed behind enabling deep learning for the community and democratizing it. And there's also educational programs that if you're teaching a course on machine learning, we can enable cloud credits for the students as well. So if you're interested in that, you can go to that link or message me. And also, of course, we are actively hiring if you're interested. Thank you. Yeah, so I don't know if the format is to have questions now or there is the next speaker. Yeah. Mm-hmm. Right. Yeah, so with respect to debugging and prototyping, I mean, you can also, you can do that with Jupyter notebooks, right? So that lets you help. Was there a very specific feature? Like we have the profiler that lets you keep track of your training, but I don't know what specific feature you were looking for. Yes. Right. I mean, so yes, it is messier to debug when there's a declarative style of programming, right? And so the goal is to enable much more imperative operations. So the idea is deep learning has a specified set of operations that if we can optimize it, so even when it's written in imperative style, that it will be enabled well, right? So that's the goal. We are not at there, but when that happens, right, it will become a lot easier for the programmer.
You said about the profiler. Is there something like TENSOR?
Yes, there's a similar one, yeah. All right, thank you.